Hey everyone, welcome back to Calculus 2. This is going to be lecture 28 of the course, and in this section we're going to begin talking about Taylor polynomials and approximations. So in the previous sections we have been very deep in the theory of convergence of series, and we're taking a slight shift to the slight left turn here, talking about Taylor polynomials and approximations, and then we're going to take that and bring it back and join that to what we've been discussing with series. So let's start in on this. Let's go ahead and jump into it. Let's call this section 4.7, and this will be Taylor polynomials. Okay. All right. So in this section, what we want to do is we want to kind of develop some ideas about how polynomials can be used to approximate other elementary functions. Okay. So that's kind of like a motivating statement, right? So in this section, we will discuss how polynomials can be used to approximate other functions. We'll say elementary functions for now. Okay. So the idea here is, let's draw a picture. The idea here is maybe I have some function f of x, and what I want to be able to identify a polynomial that approximates f. All right, so given some function f, we want to identify a polynomial p that approximates f. Now, when I say approximates f, I don't mean, we have to qualify that, we don't mean approximates f everywhere, but what we mean is that we want to be able to approximate f in a specified region, right? And the terminology we're gonna use here is kind of loose, but we want our polynomial p to approximate f in the neighborhood of c, right? C just being whatever number we choose, okay? All right. And so let's say, c is here, right? So we're going to try to find some kind of a polynomial that agrees with f in some neighborhood maybe of this value c. Okay. Now this term neighborhood, we use it loosely here in analysis. If you go into further in the math career, when you get into analysis, the idea of neighborhood is very specific and rigorously defined. But here we literally just mean kind of for values near c, right? That's kind of a loose way of thinking about it. Okay. And the terminology we'll use here in conjunction with this is that, if we're interested in p approximating f in the neighborhood of c, then what we'll say is that p is expanded about c or centered at c. Those are two kind of interchangeable ways of saying the same thing. So we say that p is centered at c, or that p is expanded about c. Okay, that's kind of some terminology there, right? And so whatever c happens to be, if c in this, maybe it's 4, then p is centered at 4, or p is expanded about 4. Maybe c is 10,000, p is centered at 10,000 or expanded about 10,000, whatever. So that's just terminology, ways of kind of describing where you're centering your polynomial. It's kind of where you're centering your approximation. Okay, and so the way we're going to generate these approximations is we're going to start by simply requiring that P and F have the same value at C. Okay. So we'll start by requiring that P and F have the same value at C. Now that doesn't do a whole lot for us. If you think about that, right? So again, just kind of drawing in my F here, right? And if this is C, there are an infinite variety of polynomials that pass through the value here indicated, right? This would be CFC, CF of C. Right, so one such would be the line that we drew up above here, something like that. Another one would be, I could come up with something like that. A third one might be like this, right, et cetera, like I could come up with these all day long, right? So this is to say that either of these drawn in what I've drawn here resembles the function f in the neighborhood of C would probably not be very accurate, right? They're equal at the value of C, but nearby they have nothing in common, right? So in fact, this one here, has an almost perpendicular slope to f at the value of C, right? So in order to improve our approximation, we will issue an additional constraint. Right, an additional constraint to use is that the derivative of f at C be equal to the derivative of P at C. All right, now what does that guarantee? Well, it guarantees something more like this, right? That, not only do the values of f and P, not only are they the same at C, but also the derivatives are the same at C, which means that the slopes are the same at C, which means that at least in the neighborhood of C, the lines are headed in the same direction, right? Whereas here, in this image down here, this highlighted one here, right, P prime of C is very different from F of prime of C, right? In particular, this one is negative and this one is positive. Right? So this additional constraint will be needed. Okay. And this is the starting point for the Taylor polynomial. Okay. So let's pull out a specific example and kind of work through how we might generate this P for a specific function and a specific value of C. Okay. And so for this one, we're going to start where, basically anytime anybody learns about Taylor polynomials, we almost always start with the example of the exponential function. So for the function f of x equals e to the x, what we want to do is find a first degree polynomial function, and the form there is going to be p1 of x. That's we're going to call it p1, and it's going to have the form a0 plus a1 of x. For it, all first degree polynomials will have this form, right? And so we want to, for the function f of x equals e to the x, we want to find a first degree polynomial function p1, this form, whose value and slope, at x equals 0 agrees with f of 0 and f prime of 0. Okay. All right, so this is kind of what we're after. We're going to, again, just basically do the thing we've just described, but with this specified function f of x equals e to the x. and a first-degree polynomial. And we're going to specify that the approximation, the polynomial P1, will be centered at, or if you prefer, expanded about, x equals 0. Okay? All right. Very good. So let's do this. Let's run this exercise quick. So we start with f of x equals e to the x. And we know that the derivative there is the same. Right? So it's a nice kind of function. It's got this property, of course. And so, of course, f of 0 equals e to the 0 is 1. And the same is true for f prime of 0. It's e to the 0 is 1. So the value of the function and the value of the derivative are the same at x equals 0. Okay. And so our polynomial P1 of x is equal to a0 plus a1 of x. Right? So we know that basically what we need is we need P1 of x, which is, as we've just defined here, a0 plus a1 of x. We need that to equal e to the x at x equals 0. Okay, so let's just plug in 0 and see what happens here. P1 of 0 equals a0 plus a1 times 0, which is equal to e to the 0, which we know is 1. Right? And so what we get here is a of 0 plus 0 is equal to 1. So that means at least the a0 term, right, that a0 coefficient needs to be 1. Now we also need the derivatives to agree. All right, so we also need P1 prime of x, which we can figure out pretty quickly, right? The derivative of this function here. Let's write it out here. Well, what is it? So this is just a constant. The derivative of a constant is 0, and then this is a1 times x, so the derivative must just be a1. Right, so we also need P1 prime of x, which is equal to a1 to equal e of x at x equals 0. Right, and so that means that, so let's plug that in. So P1 of 0 is just a1 again, it's a constant, and that needs to equal e of 0, which is 1, and so that means that a1 is equal to 1 as well. Okay, so we've got the two coefficients of the two terms of this first polynomial approximation. Okay, and so therefore P1 of x should be equal to 1 plus x. So this is a polynomial that approximates f of x equals e to the x in the neighborhood of x equals 0. So let's write that P1 of x is equal to 1 plus x is a polynomial that approximates f of x equals e to the x in the neighborhood of x equals 0. Okay, so what does this look like? Let's draw a picture here. And we kind of already drew this. As sort of this was our first example, right? So if this is our f of x equals e to the x, right? We know that's kind of what it looks like, right? It passes through the point 0, 1. And what we've established just now is that a first-degree polynomial that approximates f of x equals e to the x at x equals 0 is this guy, P1 of x equals 1 plus x. And so this is a terrible drawing, but it looks something like this, right? So basically these two would coincide nowhere except at x equals 0. Right? And then as you move away from x equals 0, f of x increases, but increasingly, and whereas P1 is a linear function and just kind of increases with this constant slope of 1. Okay, so to say that slightly more succinctly, we can see that P1 is a good approximation of f at x equals 0. good approximation of f at x equals 0, but the gap significantly widens, I guess, as we move away from 0, 1. Okay, and really in either direction. Okay, and that's okay, right? Because this is just an approximation in the neighborhood of x equals 0. So the question would be next, how can we improve the approximation? I think, really, if you were to zoom in on this, if you go get a graphing utility or go out to Wolfram Alpha and zoom in on these two functions, you'll see that they agree only in really one spot, right at 0. And then as soon as you get just a little bit off of 0, they're different, right? So how can we improve the approximation, right? So how can we improve the approximation? Okay, so that's what we want to do next. What can we do to make the approximation better? Okay, so to improve the approximation, we can introduce another constraint. Okay, so we can introduce another constraint, and that new constraint would be that f double prime of x be equal to p double prime of x at x equals 0. Okay, at the value of x equals, in this case, 0, x equals c more generally. Okay, now the first derivative, remember, the first derivative is slope, right? So by having the first derivatives agree, we are ensuring that the slope of p is the same as the slope of f at the centered value. When we introduce the second derivative, what are we introducing? Well, it's concavity, isn't it? That's kind of what's missing from our approximation that we just looked at. So let me pull this picture back up here. So you can see here, right? This line here, f, is concave up, right? Whereas P1 is just a straight line. There's no concavity to it. It's a straight line. And so the gap that begins to form here is due to one of the points, or one of the functions, f, namely, having concavity, being, having some curvature, whereas the other one has no curvature, right? It's a straight line. And so when we introduce the idea of the second derivatives being in alignment at the center value, then you're saying I want the curvature of P to be in the same direction as the curvature of F. Okay, and so that will obviously make our approximation better. So then the polynomial P, we'll call it P2, will be the polynomial of least degree that satisfies. Right, so we'll have to have P2 of x, 0. Let me rewrite that. So we'd have to have P2 of 0 equals f of 0. We also need the first derivatives, so P prime of 2 of 0 equals f prime of 0. And we want now the second derivative as well. P double prime of 2 needs to equal the second derivative of f. Right? So previously we had these two, and consequently the polynomial of least degree was linear, and so had no curvature. So now we introduce this constraint, which means we'll have to have a different polynomial naturally, but this one's going to have a value for the second derivative that equals f. right? So it means concavity will be the same. Now, we could go through this exercise. We could expand our P1 to a P2 candidate in the same manner as we found P1, right? So we just have to introduce the additional constraint that the second derivatives be equal, right? And so we could do that, and so we could perform the same exercise as above. To arrive at a P2 of maybe 1 plus x plus 1/2 x squared. Okay, again, this would be, you could arrive at this using the exact same methods as what we just used. Okay, and having done this, right, again, another picture. Bear with me here. So if this is your f, and this is your P1, so now your P2 looks something like this. So P2 is going to have some curvature. It's a quadratic, right? You can see it's 1 plus x plus 1/2 x squared. So it's a quadratic. The lead coefficient is 1/2, so it's concave up, right? And so this gap will be much less than the gap between f and P1. Right, so P2 is a better approximation of f, right? And not only here where it's centered, but also further out, right? You should expect the approximation to be better for a wider neighborhood of C, well, in this case, x equals 0. Okay, so maybe out to here it's reasonable now. Okay. All right. And so we could go even further. We could demand that the third derivatives be equivalent to one another, right? And then we could demand that the fourth derivatives be the same, and so on and so forth, right? And if we continue with this pattern, a characteristic polynomial begins to emerge here. So if we continue with this pattern, all right, and I'll just restate the pattern, requiring that the first n derivatives of P, and we'll call it Pn of x, match the first n derivatives of f of x. All right, what do we get? And this is for the specific case of f of x equals e to the x. We get something that looks like this. We get Pn of x equals, again, there's our 1 plus x plus 1/2 x squared. That part we've seen. But then we could expand it even further to 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus ... plus 1 over n factorial x to the n. Okay, now this 3 factorial, 4 factorial, this just falls out of the structure if we were to excuse me, if we were to go through and identify what all the coefficients need to be. Right, so this would be 1 over 1 factorial, this would be 1 over 2 factorial, 1 over 3, 1 over 4 factorial, etc. Right, so that's what the nth polynomial for this particular f centered at 0 looks like. Now it's important to note, this is for f of x equals e to the x centered at x equals 0. All right, it's very important to note that, if you were to center your approximation elsewhere, you would get a different value. And so in general, the approximation around an arbitrary C will look like, it'll look like p sub n of x equals a0 plus a1 x minus c plus a2 x minus c squared, right, plus a3 x minus c to the third plus dot dot dot, right, plus a sub n x minus c to the nth, right? So in our case here are a0, a1, a2, a3 had the form of 1 over n factorial, right? And we can see that I just have x to the first, x squared, x cubed, right? Because c is 0, right? If I had x minus 0, I would have the same thing as this, x. If I had x minus 0 squared, it'd be the same as x squared, right? So these terms here will differ depending on the function you're approximating, of course. But in general, expanding around an arbitrary c that is non-zero will change your approximating polynomial, but just in terms of what's inside these parentheses. Okay. And so let's think about for a second. So in the example we just looked at, you can see that the 1/2, the 1 over 3 factorial, 1 over 4 factorial, these are just constants, right? So they're not going to impact the derivatives of p of n here. So let's think about what these derivatives would look like in a general sense by using this expression here, right? So what does the first derivative look like here? Well, a sub 0 here, that is a constant, so it becomes 0. And so we start with just a1. So it's a1. The derivative of this term would be a1 times the derivative of x minus c. Now, x minus c, right? So you kind of look at this and you think, well, this is going to require the chain rule, right? At least certainly when you get up to these higher terms, you have to start thinking about that. But notice that the derivative of the inside function is always the derivative of x minus c. For all of these, it's always derivative of x minus c, derivative of x minus c. So it's always 1. So this is just the generalized power rule, and the chain rule, basically, the inside function always has a derivative of 1. And so this is just a1, and then plus 2 times a2 times x minus c, right? And then this term here, when we differentiate, becomes plus 3a3 x minus c squared plus dot 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 plus n times a sub n x minus c to the n minus 1, right? So it's very easy to differentiate these. What about the second derivative? Again, this is 0. So we start with 2 a sub 2, and then that is just 1 when you differentiate. And then it's 2 times 3a3 times x minus c plus dot 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 plus n minus 1 times n a sub n x minus c to the n minus 2. Okay, what about third derivative? Well, it'd be 2 times 3a sub 3, that's this one, plus, and then we could do the next one, we just don't have it in front of us, so we'll just dot 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 all the way out, and you get n minus 2 times n minus 1 times n sub n of a sub n times x minus c to the n minus 3. Okay, and we could, what's the nth derivative of p to the n look like? Well, it's just, I'm going to flip all of these, right? So we'll write it like this, n times n minus 1 times n minus 2. And how far out does it go? Well, times 2 times 1 of a of n times a of n. Right, so it looks like that. Okay. And so the nth derivative of an nth degree polynomial is a constant. So this is just a constant. Okay. Okay. So this is the structure that the derivatives all have. Now what happens when we let x equal c for each of these? What happens when we let x equal c for each of these? Well, just let's look at the first derivative here. well, so if we plug in x equals c for the function itself, the polynomial itself, you get a0 plus a1 times, and this will be c minus c. So this is 0. This is also going to be 0. This is also going to be 0. So Pn of c is just a of 0. Okay, Pn of c is just a of 0. What about the first derivative? What do we get for the first derivative when we plug in c? Well, this is a of 1 plus 2a2, oh, and then here you're going to get a 0. C minus c is 0. Here you also get a 0. All of the terms will be 0 except for the first one. So Pn of the first derivative of P of n evaluated at c will be equal to a1. And this continues. The second derivative evaluated at c is equal to 2 times a sub 2, right? And so on. Till the nth derivative of P of n evaluated at c is going to be equal to basically this thing here, which is n factorial times a of n. Okay. All right. So that's hopefully straightforward, right? So each of these is just a constant. Okay. And not only just a constant, but it's a very predictable constant. It's basically whatever the degree, whatever derivative it is, that take that number factorial times the nth term, or if it's the first derivative, it's 1 factorial times a1. If it's a second derivative, it's 2 factorial times a2. If it's the fifth derivative, it's 5 factorial times a5. So it's very predictable. Okay. All right. Very good. Very good. Okay. So because the value of f and its first n derivatives, right, must agree with the value of P of n and its first n derivatives, it's gonna, so basically let's just recap. It follows. Let's write this down. Let's just recap this. This is important before we define Taylor polynomials. Because the value of f and its first n derivatives must agree with the value of P of n and its first n derivatives, and specifically at x equals c, it follows that, and here's kind of another way to say what we've just said, f of c is equal to a of 0, f prime of c is equal to a1, f double prime of c over 2 factorial is equal to a2, and f of n of c over n factorial is equal to a of n. Okay, so with these here, right, with these coefficients, we can define the Taylor polynomials. Okay, all right. Okay, and so here comes, here's sort of the definition of a Taylor polynomial. Okay. So the definition of a Taylor polynomial. Okay, so if f has n derivatives at c, okay, then the polynomial, here here it is. P sub n of x is equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c plus dot 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 plus f nth derivative of f evaluated at c over n factorial times x minus c. And this is to the nth power. Sorry, this should be squared. Okay. This is called the nth Taylor polynomial for f at c. Okay. So that's the definition of a Taylor polynomial, right? And so you can see this took the form of the approximation that we detailed last time, and it just kind of flipped some of this on its head. And instead of having the a1 through a of n laid in there, we just define the coefficients as the nth derivative, we'll say the ith derivative of f evaluated at c divided by I factorial in this case. Okay, and so that's a more convenient way to think about it because it's function agnostic. It doesn't matter what function it is in that case. Okay, all right, very good. Now, a special case here, if c equals 0, right? So if c is equal to 0, then p sub n of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus dot 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 plus f nth derivative evaluated at 0 over n factorial times x to the n. Okay, and this is in the case where the polynomial is centered at 0. There's a special name for it. It's a special case. It's called the nth Maclaurin polynomial for f. Okay, so it's basically a Taylor polynomial just centered at 0 and has a special name, Maclaurin polynomial. Okay, very good. All right, so that's the definition of the Taylor polynomial. Okay, and it's a way to approximate a given function f using this form. Okay, all right, let's do some examples. Let's try generating some of these polynomials and see what's involved. Okay, let's take a few examples here. Let's find the Taylor polynomials. And we'll find a couple of them, P0, P1, P2, P3, and P4 for different function, f of x equals the natural log of x, and we'll center it at 1. Okay, so no longer centering at 0. Here we're centering at 1, and it's obviously not e to the x, it's ln x. Okay, so let's figure out, so we know just from what we just discussed that really to find this polynomial we need to identify the derivatives of f, and we also have to evaluate the derivatives at whatever c happens to be. So let's do that first. Let's start with that. Okay, so f of x is equal to ln of x, and f of 1 is equal to ln of 1, which is 0. Okay, so starting there. Okay, so then the derivative of ln x we know is 1 over x. Okay, so the derivative evaluated at 1 is 1 over 1, which is 1. Okay. the second derivative, well, you'd have to differentiate this, right? And when you do that, because this is x to the negative 1, you introduce a negative and you get negative 1 over x squared. Okay, and so that means the second derivative evaluated at 1 is going to be negative 1 over 1 squared, which is negative 1. The third derivative, again, doing the same operation here. And what you end up with is 2 over x cubed, but we're going to write it like this, 2 factorial over x cubed. Okay, and then when we evaluate that at 1, we get 2 factorial over 1, well, 1 cubed, which is 2. And so you can see what's happening here. And finally the third derivative and the fourth derivative. Wait, that was the third derivative. This is the fourth derivative. Okay, the fourth derivative. The fourth derivative is negative 3 factorial over x to the fourth. And when we evaluate that at 1, we get negative 3 factorial over 1, which is negative 6, okay? And so this is all we'll need to generate the polynomials. Okay, so we'll just need these as references to plug. Basically, we're going to plug this into the form that we just discussed. Okay, so let's recall the form. Okay, so what did we have before? We said that p of n of x is going to be equal to f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared plus dot 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 plus f to the n of c over n factorial. This is not f to the n, this is the nth derivative of f, times x minus c to the nth power. All right, so this is the form. Now all we have to do is just plug in our expressions. So let's start with p0. So p0 is just going to be equal to f of 1, which is 0. Okay, so p0 equals 0. What about p1? p1 is equal to f of 1 plus f prime of 1 times x minus 1. Okay, so what do we get there? We get 0 plus 1, so f prime of 1 was 1, and then it'll be x minus 1, right? And so p1 is, I'll put it down here, p1 is equal to x minus 1. What about p2? p2 is equal to f of 1 plus f prime of 1 times x minus 1, right? So this is, of course, this whole thing is just this. But here we have to also add in the second derivative plus f double prime of 1 over 2 factorial times x minus 1 squared. Okay, now if you kind of go through that exercise, you'd see that p2 is equal to, of course, x minus 1 up front, and then minus 1/2, right? The f double prime is negative 1, so this would be negative 1/2 x minus 1 squared. Okay, so that's p2. And continuing on to p3 and p4. p3 of x is equal to f1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared plus, and there you've got the third derivative evaluated at 1 over 3 factorial times x minus 1 cubed. Okay, and so this is really going to be the same as before. It's going to be x minus 1 minus 1/2 x minus 1 squared. That's the piece that we had for p2, plus you're just going to add in this last piece here, plus 1/3 x minus 1 cubed. Okay, and so the fact that these kind of build on each other is nice. Right, and then finally p4 of x right? It's going to follow the same pattern. You're going to have all of these terms plus, you know, it's basically, I'll just write it like this. It's going to be P3 of x plus f fourth derivative evaluated at 1 over 4 factorial times x minus 1 to the fourth, right? So this is just this guy. And so all together for P4, you're going to have x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 to the third power, and then minus 1/4 x minus 1 to the fourth power. Okay, so this will be your fourth degree Taylor polynomial for f of x equals ln of x, centered at 1, x equals 1. Okay. All right. So this is great, right? And so the idea here would be that these polynomials, and I'm going to try to draw this. We'll see how well this goes. Okay, so there's 4 of them. So let's see if I can. Let's see how bad this will be. But I mean, hopefully you can imagine what this looks like without actually, you know, seeing a great picture. Well, I mean, maybe you can, maybe you can't, right? So in each case, f maybe looks something like this. I think it looks pretty similar to this. Okay. Now in the first case, we had P1, which was linear, and it just went like this. Now in the second case, we had P2, and it's going to come up and then come down, right? So maybe this is your x equals 1, right? This is a bad picture. It would hug this line really tightly, but the curvature would be there. So this would be P2. With P3, the curve comes up, it kind of flattens out, and then it goes up like that. And then in P4, it kind of has a little bit of a something like this. Right. Now, these are terrible drawings, but the idea is that in each case, the curvature of P is changing. The number of, we know, first degree, second degree, third degree polynomials, fourth degree polynomials, they're going to have a different number of, turns, right? And so the polynomials are always going to be changing, but in each case, they're going to become better and better approximations of f at x equals 1. Okay, in the neighborhood of x equals 1. All right. Excellent. Excellent. All right, so again, try to find a, just go online, try to find a better visualization of this. I can't really draw. This is not a great example, but my point in drawing isn't to make it a great example, but just to show you that the curvature of P is always changing, but it's changing in such a way that the approximation is going to become increasingly good, better and better around the center point. Okay, very good. Let's do another example here. Let's find the Maclaurin polynomials. Let's find the Maclaurin polynomials, P4 for f of x equals cosine of x. Okay, so we just have to differentiate cosine, right? So f of x equals cos x. What does f prime of x equal? Well, that's the negative sine of x. F double prime of x would then be the negative cosine of x. F triple prime of x is going to be equal to, now it's going to flip, a negative times a negative makes a positive again, and then the fourth degree polynomial, the fourth derivative is going to be cos x. Okay, and you can see that once you're back to cos x, you're just going to kind of continuously repeat this, right? So you could quickly evaluate, you could quickly identify the coefficients for really high degrees if you wanted to, because this one has a pattern. Okay, and so that means f of 0 then is cos 0, which is 1. F prime of 0 is negative sine of 0, which is 0. F double prime of 0 is negative cos 0. Well, if cos 0 is 1, then negative cos 0 is negative 1. F triple prime of 0 is equal to sine of 0, which is 0. And the fourth degree, sorry, I keep saying that. The fourth derivative, evaluated at 0, is equal to the cosine of 0, which is 1, right? So your pattern is 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. It's just going to kind of repeat. Okay. And so P4 of x, right, remember, is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared plus f triple prime of 0 times x cubed plus f to the fourth evaluated f, the fourth derivative of f evaluated at 0 times x to the fourth. So let's plug all these in. So f of 0 is 1, and then this will be f prime of 0, which is 0. So this will be 0 times x. Second derivative is negative 1. Okay, and then the third derivative is 0 again. And then the fourth derivative is 1, back to 1. Okay, so that means P sub 4 of x is equal to 1 minus x squared plus x to the fourth. Shoot, you know, I forgot this would be over 2 factorial, 3 factorial, 4 factorial. So that means this is over 2, over 3 factorial. Sorry about that. Left a little something out there. Okay, so let's write it better here. So all in, this would be 1 minus 1/2 x squared plus 1 over 4 factorial x to the fourth. Okay. All right, so there we go. So that is perfect. All right. Okay, very good. So I think that's a good spot to stop. And next time we get together, we'll jump into a very, very cool section of calculus called a power series. And so this will be basically a series that's used to represent functions and represent them precisely. So it's very very interesting stuff, kind of probably some of the more advanced stuff that we'll see naturally for calculus 2, even for calculus 3. This power series stuff is pretty high tech and interesting. So until then, take care, and we'll see you next time.